Alright, so here we have the first question, which is based on KNN. So before solving this question, let's look at a one-liner summary of what KNN is, right? So here's the setup. We have a data set, x1, y1, x2, y2, and so on up to xn, yn, right? Where each xi is a member of Rt, the d-dimensional Euclidean space, and yn can be either 0 or 1. In fact, this is just a notation. You can use it as yes, no, true, false, 0, 1, minus 1, 1. All of them will have the same, effectively the same value, right? Because we are considering a binary classification problem. Now the question is, if I give the model a new data point, say xt, let me call that xt, how will the model obtain the prediction corresponding to xt? Which means, will it predict xt to be lying in the class 0 or the class 1? That is the classification problem, right? Okay. So let's start with how the model will go about deciding. So the step 1 would be that it will compute the distance or the distance squared between this new point xt and xi for every I, right? So for example, it will compute it for x1. It will also compute it for x2 and so on. It will compute it for the last data point xn, right? And again, we will obtain few values, right? Let me call that d1, d2, and dn. Now what will we do with these values d1, d2, dn? So the second step is that we choose the smallest di's, right? So when I say smallest di's, now the next question arises, how many di's should we choose, right? Is it just one di, the smallest di, or the two smallest di's out of the d1, d2 up to dn, or three, and so on? So the answer is we have to choose k of them, right? And we also have to choose the data points xi corresponding to those di's. So let me denote those data points in the dataset D which are closer to xt, right? Let me denote that by xt1, xt2, and so on, xtk. So these are the data points which are very close to the new point xt. Now, typically, we also make sure that k is an odd number. We don't want k to be an even number, because if there is an even number, there is a chance of a tie. So we make sure it's an odd number, and then the third step is that the prediction yt will be nothing but, we will look at what is the we will look at all of y1, or you can say yt1, yt2, and so on, ytk. Remember, this is a supervised learning problem, so we already have access to these labels, right? Why do we have access to these labels? Because we already know what xt1 is, xt1, xt2, all of these are in the dataset D. Correspondingly, we also have yt1, yt2, and so on, right? So all of them are in the dataset D. Now what we will do is that yt is chosen to be 0 or 1 based on whether 0 occurs maximum number of times among yt1, yt2 up to ytk, or 1 occurs maximum number of times among these labels, right? So among these labels, say ytj, which one occurs more? So if 0 occurs more, then we will say it is 0, or if 1 occurs more, we will say yt is equal to 1. So this is the whole prediction all about, right? Now, one thing to be observed is that irrespective of what k is, we have to compute the distance of xt to every point xi, right? So let me write that down as a note. Irrespective of k, we have to compute all DIs, right? So all of these, right? Now, this means that we will have to store all the data points x1, x2 and xn. Now let's look at the question. So the question says we have 1000 points for classification problem. The first statement says if k is equal to 10, it is enough if we store any 10 points in the training data set. That is not true, because we just saw that we have to compute the distance between every data point, and hence we need to store every data point. If k is equal to 10, we need to store the entire data set. This is true. The number of data points that we have to store increases as the size of k increases. This is again false, because just now we saw that it does not depend on k, right? The last option says the number of data points that you have to store is independent of the value k. This is true. In fact, it's independent of the value k. Furthermore, we have to store all data points, right? Okay. Alright, so here's the second question. So we have around 9 data points here, right? And the one at the center is the test data point. And there is one training data point for which the label is not known. On the other hand, we already know that the prediction for the test data point, so white test, is nothing but red. So that is also given to us, right? So now we have to find out what is the label of the training data set, which is missing, right? So again, let's quickly note that the first step of KNN is to compute the distance from the X test to every other data point, right? So one thing is that this particular distance is always under root 2, right? Similarly, this is under root 2, this is also under root 2, and this is also under root 2, right? At the same time, this particular distance is 1, this is 1, this is also 1, and similarly this is also 1, right? So basically the close points here are nothing but this data point, which is at 2, 3, right? This data point, this and this. So these 4 are the 4 closest data points. Remember, we have chosen k is equal to 4 in this particular problem, and the 4 closest data points have got label blue, red, red, and then an unknown, right? But we know that the majority of this is red, so majority of this is red, so the missing data point has to be equal to red, right? This is all the question asked for. Yeah. So this is again a question on KNN, where we are given 5 data points for training, and then there is one testing data point, right? And for each of the 5 data points, the labels are also given, right? So as step 1, so the first step is to compute the distance or the distance squared, right, of X test with every other data point. So first let's do it with X1. So this will be nothing but the norm of X1 minus X test squared, right? And this will be 1 square plus 2 square, which is equal to 5. Similarly, if I compare X2 with X test, I would obtain 4 square plus 9 plus 25 plus 100, or plus 81, sorry, which is a very big number. Again, if I compute it with X3, I shall obtain 2 square plus 1 square plus 3 square, which is equal to 14. Now again, if I compare it with X4, so X4 minus X test norm squared will be nothing but 1 square plus 1 square, which is equal to 2, and if I compare it with x5, I would obtain uh, 81 plus something something something. So these are all large numbers, right? So the smallest numbers, and here what is k? K is given to be equal to 3. So we need to look at those points, those three closest data points. So this means look at three closest data points. And what are the three closest data points here? X1, right? And then we have X3 and X4, right? So these are the three closest data points. And for X1, the predicted value Y1 is nothing but 1. For X3, the predicted value Y3 is 1. And for X4, the predicted value Y4, or in fact, not the predicted value, the label Y1, Y3, Y4 are 1, 1 and 0 respectively, right? So the majority out of 1, 1 and 0, right? So majority is 1. So since the majority is 1, Y test will be nothing but equal to 1. Alright, so here we have a question corresponding to decision tree, and from the given table in the question, we can infer that at node Q1, which is a question node, there are 100 data points corresponding to the label 0 and 100 corresponding to the label 1, right? Similarly, for the node L1, we have 50 corresponding to 0 and 30 corresponding to 1. And for L2, we have 50 corresponding to 0 and 70 corresponding to 1. Now the question says, if the algorithm is terminated at this level, then what are the labels associated with L1 and L2? So as per the uh, decision tree algorithm, any data point that reaches L1 will be given as predicted value. So prediction of xt will be nothing but maximum of the elements, maximum of 50 and 30, right? Or you can say the argmax of 50 and 30, right? So the argmax is, so the maximum is 50, so this will be given to be 0, right? Similarly for L2, it will be the same thing will happen, but so it's again argmax of 50 and 70, but here 70 is greater than 50, so this will be assigned the label 1, right? So whenever there is a new data point, right, the label associated with L1 is 0 and the label associated with L2 is equal to 1. So now we have the next question where it says, what is the impurity in L1? So this asks for an impurity in a particular node if we use entropy as the measure of impurity. So just to recall, so let us recall that the entropy, right, of particular node, so here it is L1, so this is given by negative of p times log of p, right, plus 1 minus p times log of 1 minus p, right? So this is the entropy, right? So using this we can say that the entropy corresponding to L1 would be nothing but, what is p? P is the fraction of the data points which are corresponding to the label 1, right? So that would be 30 out of 50, right, which is 3 by 5. So 3 by 5 times log of 3 by 5 plus, again I have to do, so it's not 3 by 5, sorry, so it has to be 3 by 8 because 30 by 80, right? Similarly 50 by 80 is the fraction of labels corresponding to 0, right? So I'll write it as 5 by 8 log 5 by 8, right? Now this on computation will give us, and also there is a minus sign outside the whole thing. So this will give us minus of negative 0.5306 minus 0.4238, right? So So this will be equal to 0.9544. Okay. So this is how we compute the entropy at a particular node. So now we have the next question where we are asked to compute the information gain, right, for this particular split, right? So how do we do that? The information gain is nothing but the difference between the entropy of the question Q1 and the weighted average. So let me write weighted average of entropy of L1 and L2, right? So we already obtained the entropy of L1, right? So we know that E of L1 is equal to 0.9544, right? Similarly, we can obtain the entropy of L2, which will be nothing but 5 by 12 into log of 5 by 12. Again, for all log, we are using log base 2, okay? Plus 7 by 12 log of 7 by 12, right? Now, this on computation will give 0.9798, right? So now what will be the weighted average of the entropy of L1 and L2? So the weighted average of the entropy of L1 and the entropy of L2 will be nothing but, so we can notice that out of the 200 data points, 80 went to L1 and 120 went to L2, right? So there are 80 in L1, so I will say 80 by 120, sorry, 80 by 200 times the entropy of L1 plus 120 by 200 multiplied by the entropy of L2. So this is the weighted average, right? Now this will give us 0.96856. And now what we have to do is that we have to compute the entropy of Q1. So now at node Q1, the case is such that there are equal number of data points in both the classes 0 and 1, right? So that means that the entropy of Q1 is equal to negative of half times log of half plus half times log of half, right? Now this will be equal to 1, right? So in fact we have obtained the highest entropy when the data points are equally divided between the classes, right? So now what is the information gain? So the information gain is nothing but the entropy of Q1 minus the weighted average of the entropy of L1 and the entropy of L2. Now that will be equal to 1 minus 0.96856, which is nothing but 0.032. So this is our final answer. So here we have the question. If a test point comes up for prediction, what is the minimum and the maximum number of questions that it would have to pass before being assigned a label? So essentially this is the decision tree, and we can observe that there is so we need to look at where the leaf nodes are, right? So here the labels are 1 and -1. So the leaf nodes are sitting here. This one, this one, this, and all these, right? So now we have to see, we can observe straightforward that if a particular test point gives yes to Q1, right, and then no to Q2, then it would be assigned the label +1, right? Now what does that mean? That means that this is kind of the minimum number of questions that a test point will have to pass through, right? The minimum will be equal to 2. Similarly, there is one more minimum which is along this path, right? But this is also 2, right? There are 2 questions. Similarly, the longest path from the root node, so let me call this the root node, right? And the others are leaf nodes, right? So how did we obtain minimum if equal to 2? This is the smallest distance from root node to any leaf node, right? So similarly, we can obtain that for the maximum, the farthest leaf node is say this or this one or this one, right? These are the farthest ones. So we can say we go through 1 question, 2 questions, 3 questions, 4 questions, and then we can obtain yes or no accordingly, right? So the maximum is 4 questions. And how did we get this? This is the largest distance from the root node to any of the leaf nodes, right? To any of the leaf nodes. So this is how we obtain the maximum and minimum number of questions that a particular test node, a test point, will have to pass through, right? In order to be assigned a label. Alright, so here we have a question on impurity, right? So as a first case, let's take the impurity to be the GINI index. Alright, so here we have a question on impurity. So as a first case, let's use the GINI index impurity. So the GINI index impurity, let me denote that by GP is given to be 1 minus P square minus 1 minus P whole square, right? So this is the GINI impurity for a binary classification, right? For a binary classification. Now, in fact, if there are multiple classes, right, then we can represent it as 1 minus summation of pi square, right, where I is each class. So let me assume that if there are m classes, then I running from 1 to m, right, where m is the number of classes, right. So for each class, there is a probability associated with it, which is pi, and that is the pi being used here, right. So this is the GINI index in a general setup, right. But this is the question is a binary classification problem, so it's GP, right? Now let's try to understand what happens to GP when P increases and so on. So let me take the derivative of GP, right? That will be nothing but minus of 2P, right, plus 2 times of 1 minus P, right? Now that is same as 2 minus 4P, right? Now we need to analyze when this is positive, when this is equal to 0, and when this is negative, right? So we can say that this holds when 2 is greater than less than 4P, that is P is less than greater than 1 by 2. So what does this mean? This essentially means, so we can say that when P goes from 0 to 1 by 2, right, the value of GP, the value of G prime P is positive, which means GP increases, right? Similarly, when the value of P runs from half to 1, the value of GP decreases, right? So this means that GP attains its max value at P equal to half, right? In fact, the graph of the GINI index looks similar to the graph of the entropy, right? It will be something like this, where this is 0.5, this is 1, this is 0, and at 0.5 it takes the value 0.5. Okay, the GINI index. So coming back to the question, we can say that the last option is definitely correct. The impurity of the node does not depend on P. This is wrong because it does depend on P. As the value of P increases from 0 to 1, the impurity decreases. This is false. In fact, it first increases, then decreases, right? So both of the first options are false. Alright, so here we have a question on linear classification. It says this classifier misclassifies 4 points. What are those 4 points? It's this one, this one, this, and this, right? So essentially, whatever points lie to the downside of this black straight line, right? They are classified as green, and whatever lies above are being classified as red, right? And they ask what is the possible value for the weight vector. Now, since we know that this black line is the linear separator, the weight vector is always orthogonal to the linear separator, right? So the weight vector will be along this direction. And this means that uh, it is in the negative x direction and positive y direction, right? So negative x direction and positive y direction. Now that can happen only in the second option, which is why the second option is correct. Now we have a question on decision tree algorithm. So which of the following are valid decision regions for a decision tree classifier for data points in R2, right? So one key important thing about decision tree algorithm is that so let me write that decision tree algorithm DTA partitions the feature space So what is the feature space in this example? It is R2, right? So here R2 into horizontal and vertical half spaces. So half spaces need not mean that it's exactly half, but it will draw horizontal and vertical lines uh, to separate the data points. So that is the whole idea, right? And now, and why is this the case? Because at every point it's asking a question of less than or greater than, right? So at every point it's drawing either a horizontal line or a vertical line, depending on if it's asking a question based on x1 or x2, right? So that is the whole idea behind it. If you want further illustrations on the decision tree algorithm or any of the other algorithms, let me know in the comments down below. Okay. So in these options, the first one has only horizontal line, so this corresponds to a DTA. The last one also corresponds to a DTA, and the second one also corresponds to a DTA, right? Because all of them are horizontal or vertical lines. But the third one does not correspond to a DTA because there is a diagonal line as well, right?